MLP architecture. So as we can see that MLP is an advanced version of a perceptron. So in this we have a series of perceptrons which are used to get the output for a given input. So if we see there are there are three parts of an MLP. First of all, it is the input layer which takes the input of the data. Then there are some hidden layers which processes the data, and then there is finally an output layer which gives us the output. So moving on to some properties of the architecture. So first of all, there is no connection within the layer. So although we have multiple layers in the perceptron, but we ensure that within layer, no two layers are connected directly. The only kind of connection we have is from one layer to the other layer. Second is that never the input layer and output layer are directly connected, because we have to do the computations in an MLP. So these computations are performed by the hidden layers. So we'll have to pass the inputs to the hidden layer, and then the computations will happen here, and then the output will be presented. So input and output cannot be directly connected. Another is that fully connected between layer, because MLP are generally used to perform classifications over a non-linearly separable data. Hence, if we connect every layer, if we connect each and every input to each and every hidden layer, it will give us a higher chance of getting understanding the pattern clearly. And often more than three layers, but this is like the number of hidden layers is like a hyperparameter which we will have to tune. But generally, if the data is complex enough, the having more hidden layer is preferable. And last is that it is also important that we have non-linear activation function within the hidden layer, because as MLP, as we have seen that perceptron is able to classify linearly separable data, but if we take linear activation function within the hidden layer, then MLP would also be not able to classify like non-linear separable data. Hence, if we take non-linear activation function, it will have the potential of classifying non-linearly separable data. Moving on. So for the hidden layer, so in MLP, the actual computation occurs in the hidden layers. So in hidden layers, we can take non-linear activation function, as I had discussed previously. So the types of those functions could be like here. First of all, ReLU, rectified linear unit. So this is a function which gives us it is 0 for any values less than 0, but it is exactly that value if the value is greater than 0. So it is a max of 0 comma x. So some of the pros of this ReLU function is that it is very computationally efficient, because we don't have to do any kind of calculation. We just have to check that whether the value is less than 0, so it will output 0, and if it is greater, then it will output the exact value. So it is computationally very efficient. And also instead of ReLU, if we use sigmoid, in sigmoid we have a problem of gradient, vanishing gradient, but since ReLU has a constant gradient because its gradient is 1 because of x, so it doesn't have that kind of problem. So it is a pro, but it has a con of since it is almost 0 for any value less than 0, so there is a problem of dying neurons, because of which some neurons will become inactive during the training process. So it's one advanced version is Leaky Lulu, so it's a little bit modified version. In this version, what we do is we multiply, instead of just outputting 0 for any value less than 0, we just multiply it with a factor of a small factor like alpha. Here alpha is 0.01 times x. So in this case, we are it still does not have a vanishing gradient problem, but it solves the problem of dead neurons, because the final value is not 0, it is multiplied by some factor alpha, so gradient becomes alpha. And finally, we have also a tan h hyperbolic tangent. So this activation function is helpful if we need to produce the outputs which are zero centered, from if we take sigmoid, so sigmoid produces output between 0 and 1, but if we want the output to go into negative domain as well, so we can take tan h. So but still tan h has, because if later on I'll show the graph of tan h, so it still has a vanishing gradient problem. So that's it. If we want the output to be 0 centered between minus and 1, we can use tan h. So that's the graph of all these three functions. First of all, we have ReLU, so we can see that for any value less than 0, it is almost 0, almost exactly 0, and greater than 0, it just is a linear line. For leaky ReLU, we can see that as we are multiplying it with alpha, so we don't see exact 0, but it is having a gradient, not a 0 gradient. And finally, tan h, we can see it is 0 centered, because we have it is going from -1 to 1, and as I was saying, it is suffering from vanishing gradient problem, because at the later values you can see that the gradient almost tends to 0 here and here as well. So another thing is that in architecture of MLP, we when we train the when we train the network, it depends on what kind of technique we use to train, and that technique can be of and that technique can rely on optimization algorithms. So that optimization algorithm can be of various types. So here I've discussed basically main two types. So first of all is stochastic gradient descent. So stochastic gradient descent is an optimized version of gradient descent algorithm. So in gradient descent, what we do is we take the complete training data set at once and then modify our neurons based on those completed training data set. But in stochastic gradient descent, we take each and every point at a time or a small set or batch of point at a time, and using those we calculate the gradient and then update our weights continuously in order to get the convergence. So that's the stochastic. And then we have Adam optimizer. So what Adam optimizer is just an extension of stochastic gradient descent in which we incorporate two terms. The first term is a momentum term and the second term is a bias correction term. So the variance term. So the momentum term, what it does is it gives us a better way of updating the weights. So we can see that momentum term is nothing but beta times momentum of t minus 1, and here gt is the represent the gradient at time t. So using this, it is a better way of calculating the updating the weights. So that's the Adam optimizer. And finally, we see that how number of hidden nodes affect our affect our training of the model. So if we have like one hidden node, so in this it is basically like a perceptron, so it is not able to classify our data. It is simply a straight line. But as we increase the number of hidden nodes, our MLP is able to classify is able to classify this is a non-linear data, so it is able to classify non-linear data. And if we increase the number of hidden nodes to very much, so we can also see that it can lead to overfitting, because here now it is learning the errors of the data as well. But this is clearly an overfitted training trained model. Hence we can see that the number of hidden nodes are how much hidden nodes we take will depend on how well our MLP is trained over the model. It can lead to underfitting, overfitting, or proper fitting based on the number of hidden nodes.